Good day, everyone, and thank you for joining my talk. My name is Alessandro Tunas. I'm from the School of Physics at the University of Sydney. I'm also with Sydney Nano and the Institute of Photonics and Optical Science. The title of my talk is The Nonlinear Coefficient for Lossy Waveguides, Which Expression to Use, and discusses some recent work done with my colleagues Gordon Lee and Martin Sturck. This being a nonlinear optics session, let me just briefly review some of the background. And what we're interested in at a fundamental level are the photon-photon interactions mediated by a material. And we're just going to start with the bulk case. And so the starting point is the Taylor expansion of the nonlinear polarization, which contains susceptibility terms, chi1, chi2, and chi3. And this Taylor expansion contains a linear part and a nonlinear part. And in this talk, we will only be interested in chi3, the third order susceptibility, which will be the only term contributing to the nonlinear polarization via what is known as the Kerr effect. So chi3 is the most fundamental nonlinear parameter, but we are often interested in N2, the nonlinear refractive index, which is related to chi3 via the permittivity and some other constants. And so this parameter then tells you by how much a linear refractive index changes as you increase the intensity. So if we plot the change in refractive index as a function of intensity, the slope gives you the nonlinear index N2. And so this approach will be used later in a slightly different context, which is why I'm introducing it. And specifically, we want to consider this effect in the context of waveguides. So how do we generalize this nonlinear index change when we consider a waveguide? So the simplest case, which is the most studied due to its ubiquity, is that of a weakly guiding optical fiber. So this is formed by a silica cladding with a slightly doped silica core. And in this case, you have a mode with a propagation constant. And so generalizing the previous slide, we want to know by how much is the propagation constant changing as we increase the power. And this is encapsulated by a new parameter, gamma, that is no longer trivial and needs to be analyzed in some detail. So this parameter is known as the nonlinear coefficient, which generalizes the nonlinear index to the case of waveguides. And you find this commonly in the nonlinear Schrödinger equation, which governs pulse propagation inside a nonlinear dispersive medium. So gamma contains k naught, which is the free space wave number. You also have an N2, which is the material property, and you have an effective area that tells you how well your mode is confined. And this expression holds true for a weakly guiding optical fiber where everything is well behaved. So there are only small variations in the material. You can approximate your fields as scalar quantities, and there is almost no loss. So in this case, things are rather simple. Now, the problem kicks in when we want to miniaturize our waveguide. And so the most extreme example of this is in the context of hybrid plasmonic optical circuits, where you have many different material giving rise to modes that are no longer approximated by well-behaved scalar fields and which are tightly confined within nanoscale volumes. And so I have just included two examples here to highlight typical material combinations and geometries: silicon, silica, gold, graphene, and so forth. So there has been quite a lot of interest in using these kinds of devices for compact wavelength scale nonlinear optics for integration into existing next generation optical circuits. In recent years have been marked by an interest in so-called epsilon near zero materials that also exhibit modes that are lossy and tightly confined and have huge nonlinearity. So in these scenarios, we actually find ourselves in the opposite situation to the one I just described. In every single way, there is high loss due to the metals, there is strong confinement due to plasmonics, and all of the materials involved are vastly different. And so the problem we are addressing is how to quantify the nonlinearity of lossy, strongly guiding waveguides. And to understand this, we're going to start with the simplest possible case, a surface plasmon polariton, which is a propagating surface wave at the interface between a metal and a dielectric. And this will give us insight into which is the most appropriate way of evaluating the nonlinear coefficient. Now, this problem has been addressed by a number of different authors. The most common used approach is a perturbative one. And what this means is that the nonlinearity is treated as a perturbation. So the increase in power leads to a nonlinear change in the material. And so during this change, it is assumed that the propagation constant changes slightly, but that the mode profile does not change. So for example, if this is the mode that we are considering, surface plasmon polariton, as we increase the intensity, the mode profile stays the same, but the propagation constant increases by some amount. And so the nonlinear parameter is constant. And so different authors have used this assumption in some form to obtain an expression for gamma. So Afshar developed this approach for lossless, strongly guiding waveguides. And a similar approach was then applied by Marini et al. To lossy plasmonic cylindrical structures, leading to a similar formula for gamma. LiDeLeon et al. Use a green function formalism to lossy layer geometries, such as thin films. Barron et al. Directly solved the nonlinear wave equation with some perturbative approximation. And Lee et al. Later developed the Afshar method further, but using an unconjugated reciprocity theorem. And I should point out at this stage that one of my colleagues, Martin de Sterk, who is a co-author of the conference proceeding associated with this talk, also worked on the Lee approach. And finally, Lysenko et al. Used a phenomenological model, which is based on the weakly guiding case. And so there are many approaches to calculate the nonlinear coefficient, and all lead to different expressions. And when we started working on this, we were confused about which might be the best one. And to verify what the best approach might be, we need to use a numerical non-perturbative approach as a way to compare with the perturbative approach. And so in this case, you assume that both the propagation constant and the modal fields change as you increase the power. So in this case, there is no approximation with regards to the mode profile. So you start with the plasmonic mode, you increase the power, and this increase in power changes the permittivity, and here it's the permittivity of the metal. And this change in permittivity, therefore, also changes the mode. And so in this case, the propagation constant is a more complicated function of power. And there are two approaches worth mentioning that do this procedure, and the first is due to de Giron. And in that case, the nonlinear problem is transformed into a series of linear problems, which in essence perform the numerical version of the process that I've just described. Maslov and others have shown that by just performing the iteration once, you get the right solution with sufficiently high precision. But all of this assumes, of course, that the procedure converges to the nonlinear mode, which in the cases considered in this talk, it does. Note that in order to compare with the perturbative approach, the non-perturbative approach requires considering the slope of gamma as a function of p for p tends to 0. So armed with these tools, we have a numerical approach that allows us to compare with the analytical solutions for the nonlinear coefficient. So taking an air-gold interface as an example, we want to calculate the gamma of a surface plasmon. And this, for example, is the form of gamma obtained by Lee et al. And notice that this expression contains only linear fields. So E and H are the electric and magnetic fields. And chi3 is the chi3 of the materials involved, which you can measure independently. So once you have that, you can obtain gamma. So even though this is a complicated function, it can be easily obtained with any numerical solver. So in the case of a surface plasmon polariton, the propagation constant and the fields can be obtained analytically. And this allows us to obtain gamma itself analytically for comparison with the numerical method. So I should just point out here that X is the propagation direction and Z is transverse. So this integrates along the transverse. And we will now compare all of the methods I've described. So in terms of the linear properties of the surface plasmon, we will be taking tabulated values for the permittivity of gold. The permittivity of air is taken to be 1. And although our method is agnostic to chi3, as an example, we take the chi3 which follows from a theoretical model reported by Marini et al. And in particular, we are considering the interband region of gold, where the plasmonic losses are highest, to test this theory under extreme conditions. So we can now calculate gamma analytically and compare the different methods. So Lee et al. Leads to the following expression for gamma. We look at the real and imaginary parts as a function of wavelength. And we notice a resonant looking feature in the interband region. However, comparing other methods such as that of Barron and Afshar and Marini, we see that they are quite different from the expression of Lee. I would like to point out that at longer wavelengths, all three methods lead to approximately the same answer, to within a factor of 2 or so, but not so in the short wavelength interband. And so if we then look at DeLeon, we find that DeLeon and Lee do agree in this region. And so by comparing with the non-perturbative numerical approach, we find that Lee and DeLeon are the ones that best describe the nonlinear coefficient. And so we have two potential expressions for gamma. And so we have the finalists, to all those that are missing the Euro 2020 tournament, Lee and DeLeon, which I show here again for the surface plasmon polarity. So in their paper, DeLeon also calculates the gamma for the modes supported on a thin gold film. And so in the case of a thin film, two modes are actually supported: a symmetric long-range surface plasmon polariton, LRSPP, with low loss and low confinement, and a short-range surface plasmon polariton, SRSPP, with high loss and high confinement for these thin films. So if we look at just the long-range surface plasmon, the Lee and DeLeon method end up overlapping quite well. And most likely due to the fact that there is low loss, which makes the green function formalism of DeLeon reasonable and appropriate. And both of these methods, again, agree with the non-perturbative approach. Notice, however, that the gamma is very small, 10 to the 6 times smaller than the semi-infinite case. So if we now consider the short-range plasmon, the gamma is orders of magnitude larger, and we see some deviation between the Lee method and the DeLeon method. But when comparing with the non-perturbative approach, we find that Lee shows the better agreement. So we have found Lee to be valid even when the imaginary part of an effective approaches unity. And in fact, we are yet to find a scenario where Lee does not work. And so we can conclude that Lee provides the most generally valid non-perturbative analytic expression to use. And this allows us to look a little more closely at the relationship between the chi3 of the gold and the nonlinear parameter of surface plasmon. And so the insights obtained show that this relationship is anything but trivial. So on the left, I am plotting the real part and the imaginary part of chi3 at different wavelengths. So for example, at 400 nanometers, my chi3 sits in this quadrant. So if we then go and calculate what the corresponding nonlinear coefficient is, we observe a non-trivial rotation and transformation in the complex plane. So you can be in a situation where you have a purely real gamma with a generally complex chi3. And vice versa, you can have a purely imaginary chi3 when you have a complex gamma. And this means that depending on wavelength, you could have positive and negative nonlinear phase shifts and also nonlinear absorption and saturable absorption. So this allows to access quite a lot of rich physics with the system. And so although this might seem surprising, if we go back and look at how N2 and chi3 are related in the case of bulk gold, so for example, just a bulk gold film, we see that the denominator contains a complex number via this metal permittivity. And so this corresponds also to a rotation in the complex plane. And so in the waveguide case, things are a little bit more complicated, but this is an equivalent non-trivial transformation in the complex plane between the chi3 of the constituent materials and the nonlinear coefficient of the waveguide. So in conclusion, we have established the nonlinear coefficient for lossy waveguides. It has the following form, where x is the propagation direction and z is transverse. And for a two-dimensional waveguide, the integration happens along a 2D plane rather than along a 1D line. We have found what the preferred method for gamma is via systematic comparisons between perturbative analytical methods and non-perturbative numerical methods. And we have found that the Lee method is broadly valid for arbitrary waveguides, whereas the DeLeon method is valid for layered geometries and could be useful when considering finite beams. The relationship between gamma and chi3 is far from trivial and requires considering the complex nature of all optical susceptibilities. And this gives rise to some rich physics, such as saturable absorption, optical limiting, positive, negative, nonlinear phase shifts. And this is particularly important for highly nonlinear efficient nanoplasmonic devices that use metals and highly nonlinear materials in them. And we hope that these insights resolve some of the confusion in the literature and will help future study on lossy integrated waveguides, especially those containing highly nonlinear psi near zero media. And with that, I thank you for your attention, and I'm happy to take any questions you may have.